Okay, thanks for the introduction. Yeah, so I'm also like a first year PhD at Berkeley. Yeah, my past research is on 3D vision models and the application of those models in robotics. And as a first year PhD, I'm switching my research a little bit. So now I'm working on like two projects, one on vision language navigation model, another one on simplified RL for textual manipulation. Yeah, so those are my research, but today I'm trying to give a talk on a pretty different topic on word model. So I'm still learning this area, so this talk will be some tentative views instead of like finished positions or rigorous research, okay? Yeah, so there will be some hot takes that are not verified. They're more like hypotheses, okay? Yeah. So when people talk about like word models, the term can refer to a lot of different things. Some people refer to it as 3D models like nerve or Gaussian splats. Some refer to like video generation models. Some as dynamical systems, and even physics simulators can be considered a word model. And each of these directions captures something useful, but I think it's still quite unclear what kind of word model we actually need for general purpose robotics. So the question I want to think about in this talk is, what should a word model model? Yeah. And analogy I like to use is like this story of several blind people trying to figure out what's the object by touching different parts of the elephant. The person that touched the leg knows it's a tree, the person touched the body knows it's a wall. So I feel like this is kind of similar to the state of art of like research on word model, right? Each person has a different definition of word model, and it probably captures part of the whole truth about the word model for robotics. Yeah. And the more interesting question here is, what kind of representation is useful for the downstream requirement, for example, for robotics applications? Yeah. So this is like the current kind of landscape. I feel like there's like a JPA, dynamics, video generation, 3D Gaussian splats, and physics engines. Yeah. So in this talk, I will have three hypotheses. The first one is all word models are abstractions. Some are useful. So the goal is not actually to build a very good word model that looks great or whatever, but it should be useful for the downstream robotics task. The second hypothesis is that different representations preserves different useful structures. So maybe the final answer is not a single model. Maybe it's like a modular structure of multiple models combined and interconnected. So yeah, so that's the third hypothesis. Robotics may ultimately need multiple kinds of models, not just one. Yeah. I hope like maybe those hypotheses are not true, but I hope at least it will help us better understand what's the desired properties of word models for robotics. So yeah, the first section I'll talk about is word modeling as abstraction. So this is in spirit of the Leonard Savage's book, The Foundation of Statistics, and Oliver Brock's talk. So Oliver Brock is a robotics professor at the Technical University of Berlin. And he mentioned about this book, The Foundation of Statistics Lab. Also the book about small world. So small world is an abstraction of the big word, but it's still useful for downstream decisions.
Smile, you're being recorded.
Okay.
Smile, you're being recorded. Smile, you're being...
What?
Okay.
There's a camera.
Oh.
There's a camera.
Okay.
Forget
AI
about it.
technology. It's actually robots that are not very intelligent. Okay, so the first point that the author made in this book is the word is relative to the task. So the main point is that we should not try to model the whole word, because firstly it's not trackable, and secondly the whole word will have information that is useless for downstream decisions. So by its definition, the word should be the object about which the person is concerned. So it's really about the word that is closely related to the task. And the state of the word is description of the word that leaves no relevant aspect undescribed. So in robotics, it's we know that it's important to have the right states for the tasks. And for whole body control and direction manipulations, we probably need the very different states to complete those tasks with high performance. So the second point we made in this book is small words are acceptable and desirable if they preserve these stations. So in robotics, this gives like a very clean principle. So the question is not about how we can model the most of the word accurately. The better question is, what is the smallest word in which the robot can still make right decisions? So this is what actually made the modeling very hard, and there's like 100 years of mathematical and statistical modeling literatures on how we do modeling. And one of the picture I'd like to show here is like, this is New Yorkers' view of the world. So you can see for New Yorkers, if you know the Manhattan area is very good, but cross the Hudson River, you probably only know a few mountains. And across the Pacific Ocean, you know, okay, there's a few countries there. And for a person who lives in New York for all his life, this is like a totally good world model for him to live with. So this is example of why we want some abstractions, and it's still good for robotics. And the small word here doesn't necessarily mean small model. So in my opinion, those 100 billions of parameters like large models are still a small model compared to the complexity of the actual physical world. So so basically small word here can mean those big models. One argument against making abstractions is that we want to build very general purpose robots, which means we want a single word model that can achieve a lot of tasks. So maybe a lot of details are necessary, and we couldn't make abstractions. So the question here is, can small word generalize to general purpose robots? And there are several evidence showing that general tasks can sometimes be done with like very abstract and low-dimensional information. So in this paper, many perception tasks are highly redundant functions of their input data. The tasks are classical computer vision tasks. For example, doing classification on ImageNet, doing semantic segmentations, doing depth estimations, or optic flow estimation. And what this paper found is that for all the images in the data set, you can do Fourier transform to decompose it into different frequencies. And it makes sense that if we use the top 15 frequencies that are most related to the image and use that to train the classification model, it will have high accuracy, which is about 73%. But what's surprising is that even if we use the 30th to 45th frequency, so those are the frequencies that are very unrelated to the image. If we use those features to train the classification model, it can still achieve like 65% accuracy. So it means that there's actually some low dimensional structure in all those data and tasks that we can leverage for achieving those tasks. So that's why like a small word model can also generalize to more general purpose robot tasks. So in summary, like the hypothesis or my tentative view from this section is word modeling is basically about abstraction. So word modeling may be the best understood as the art of constructing a small, useful, and task-relevant word for reasoning under uncertainty. And the interesting question here to think about for word model for robotics is what information to keep in a word model for robotics and what information is missing in different methods of current word models. So basically, instead of choosing video models over Java or vice versa, we probably should think about, so what's the pros and cons of each of these methods. Yeah. And now let's go to the second part of the talk. So in this part, I'll give a few samples of word model methods and discuss how we can think about the difference between those methods. To make the discussion more concrete, I want to use the general definition of word model. So we consider a word model as a dynamic system that predicts the future from the current states and actions. So this is actually a very general formulation because for any word model, you can consider the representation as a state and you will have some actions. So for video generative models, the state will be the frames, obviously. The action will be the task instructions, for example. So, yeah. And for like 3D representations, the state will be the 3D motion, for example. And for physics simulators, obviously there's a state that is tracked in the physics simulation. Yeah, so the first sample I want to give is Pi.7, the most popular style for this week. So this is a big architecture. What I want to focus on is on this word model part. What they use is the BEAGLE model, which will take the current observations and the subtask instructions. Then the model will edit the image and generate sub-goal images. And those sub-goal images are used as a condition for the low-level vision learning action models to know like what should be done next. So here the word model is basically in the 2D images domain, and I would hypothesize that this kind of image models, the mainstream is about semantics. So in those models, it captures a lot of semantics about what you need to do next. And that's why the Pi.7 method is successful for using those video generative models to generate those sub-goals, which are about like the semantics of future tasks. And there are also a few other benefits of using video generative models. One is that we have a lot of 2D data, so it is much easier to train a word model like in the 2D representation than 3D or physics. Yeah, obviously, and there are some the weaker side of video generative model. So it's mainly about that those 2D representations doesn't capture very precise geometry, motion, and physics, and typically they predict plausible future observations instead of like underlying physics. But this is also like a very controversial statement because some people argue that the video models will eventually learn the physics somehow. Yeah, the second paper I will show is called Dream to Fly, model-based reinforcement learning for vision-based drone flight. So in this work, the state of the dynamic system, or like the representation of the word model, is a latent state, which are extracted from the motion and the input images from the robot. Yeah, so their method is as follows. You will firstly have a OK policy for drone racing. You will run this drone racing policy in the environment for a period of time to gather some data. And from this data, you can train a word model. So specifically, given those data, you can do encoding of those observations into latent embeddings. And then you train a predictive model to predict the next latent embedding given the current embedding and the drone actions. Yeah, so the second step is this word model training. And after this word model training, you can basically use this word model as a simulator to train the next round of the RL policy. And after you train the next round of RL policy, you will go back to the first stage to do data collection. So it turns out that if you do this for several iterations, you'll get a pretty good drone racing policy. Yeah, and here, although the word model is in the latent space, so it's similar to Jetpack, I would say it's still like 2D or like an image-based generative model because the input and output are all images. So probably a lot of information and caps are from those 2D images instead of 3D structures, right? Yeah, another additional thing this method do is that the action for this word model is actually the low-level drone control actions. Instead of like in the pad 0.7 work, the actions we can consider it as the subtask instructions. So in this work, by supervision based on the low-level control tasks, the word model learns something about the dynamics in addition to the semantics. And that's why the drone racing policy, which is highly dynamical, can work based on this method. And the third example of the forward model is a 3D representation. So in this work, we're constructing hand-cut objects in 3D from image and videos. What they do is that if we have video frames, we can extract the 3D hand geometry and objects and the hand-object interactions. So in addition to the semantics that we get from 2D models, in these models we get the actual 3D motion of the hand and objects, and also a little bit flavor of the physics, the interactions between the object and hand. Another good thing of those 3D models is that they can solve the problem of occlusion. So if you have a 2D image and you don't have proper priors, you don't know what would be on the backside of the object. But if you learn a 3D model, it will learn the 3D objects like no matter which view you view it. So it solves the problem of occlusion. Yeah. Another thing about 3D representation is that it doesn't depend on view. So, right? So because view is a projection of 3D to 2D. If we work on 2D domain, sometimes we need to care about view dependency. But if we work on 3D, that problem is less. Obviously, there are some challenging parts for those 3D representations. We don't have that much 3D data, so training those models are very hard. So for example, there's a recent work from Meta called SAM3D. They train a model to extract 3D assets from images. They have to collect and use a lot of their own 3D data to make this model work, instead of like leveraging the internet scale data. Yeah. So the last example I'll give is SimReal RL with like physics simulator. So here the word model is basically a very good physics simulator. And the one thing we get from those physics simulator is like privileged information about the states of the robot. So it's relatively easier to train the RL policy in this simulator. And because the simulator have like physics in it, so this policy can actually be grounded in physics and control level, in the control level. The problem of this method is like the simulations are typically a little bit different from the real world, so there will be something called sim-to-real gap. What people do in this case is mainly about domain randomization. The big idea is that we know that some parameter in this simulator is wrong, but we know that if we perturb these parameters a little bit, maybe the real world parameter will be lying in this distribution. So basically we randomize a lot of parameters in the simulator and make the policy robust to this perturbation. And hopefully it will work in the real world. Yeah. And it turns out it does work in the real world in a lot of cases. And yeah, so like across the 4 examples I gave, we saw examples of 2D image representation, latent representation, 3D representation, and here 3D plus physics representation. And when I was thinking about this problem, like which word model is better for which task, this is like a table I made. Hopefully it makes sense. If it doesn't make sense, please ask me questions. Yeah, so we can think about like a robotics task at different levels, like the semantics level, pneumatics level, physics level, and also how much data we have, right? And as you can see, like each word model have different strengths. Maybe the question is not about which model is correct, but how we combine those models to combine their strengths. Obviously, like a lot of recent methods tries to combine those paths to make the model stronger in multiple aspects. For example, the Pi 0.7 model, right? Although it's not like a pure word model, the VLA part is really about grounding the semantics into the physics and control. And then adding on that, they use this kind of image word model to generate subgoals. So use this model to help fix the weakness of the semantic side. Yeah. So the point is that word model is useful only relative to the downstream structure it preserves. And maybe we need to combine them. Okay, the last section, looking forward. So this is like my view on how word model will look like in 5 years. So at the end of my PhD, yeah, hopefully it's correct, or I might need to write it in 6 years instead of 5 years. Okay, so the hypothesis is that maybe you need to move from the end-to-end dream of word model to modular structure. Because as you can see, that all the successful systems often model some right slice of the word instead of the whole word. Some are strong at semantics, some are strong at motion, some are strong at interactions and physics. And if we look at the past success in modeling, there's always like this trend from end-to-end dream to modular structures. At the beginning, people think we have a single autoregressive model for language modeling. But then it turns out that for current all the VLM models, there are a lot of additional structures we add, like the MOE, different tokenizers, different encoders, and different training stages, like pre-training, post-training, mid-training, right? And another example is VLA, right? The hope of VLA at the beginning is like we have an end-to-end model that input VLA and output vision language action. But turns out there's a lot of design choice that people have to make to make this VLA paradigm work. The example is like a Pi 0.7. They have this low-level vision language model, but they also have to have a high-level policy. They have to have a word model to generate subgoals. Yeah, so seems like there's always a trend from the end-to-end dream to more careful engineering of the modules to make things actually working. Yeah, so eventually, this is my current bet, but it's still an open question, right? Eventually, word model for robotics may also converge to a modular system where different models are combined together for general purpose robot. For example, probably we'll have a high-level semantic word model. We'll have some geometric motion models to capture the motion, and in the lower level, we'll also have some policy that really turns the plan into the control signals. Yeah, and I want to show the last reason that's why I think this modular system is more reasonable. So I would like to consider the task of a trip to New York, right? The option one is like you build a model that predicts the entire 10-hour trajectories of videos in full details, including how you book the flight, taking the Uber to SFO, moving through the crowd, finding the current terminal and get embodiment plan and so on, right? There's another option, is using different maps and abstractions for these long horizon tasks. So we can use a VLM model to book the ticket. We have some local geometric models to avoid people so we don't collide with other people. We have a low-level control policy to hold the coffee. We have a map to go to SFO. And here, maybe we can use this map to navigate in New York, who knows? Right? So this is like, yeah, one example why I think like some modular structure might be useful. So in conclusion, what kind of world model does robotics really need? This is a very open question. And so as a researcher, I want to ask some interesting questions that help us to move in towards the final goal. So I feel like the scientific question here is really what information and structure we need to preserve in the world models. And there's also the engineering side of this question. How can we leverage the existing data and resources to preserve those information and structure? Yeah, and the conclusion, I do not have a confident answer, but I think at least asking and thinking about those questions would help us moving towards a shared goal of like a robotics world model. Thank you.
Okay, some quick questions. So what do you think, like, which aspect will the model benefit most? Like for data generation, or do model evaluation, or just regularize the representation for better policy learning?
That's a good question. So you're talking about like how we should use the world model, whether use the world model for evaluation or for training or
yeah, for data augmentation or evaluation, or just it's something to regularize the latent, and this latent is better for policy learning.
I see. So I feel like the answer might be both. So I think like a world model is kind of like a very strong prior about how the world works. So it will definitely help the training. So for example, if you have a world model that can very well predict the sub-goal, right? It is like a very strong training signal for what should be the next low-level action. So that's why I think world model is very useful for training. And it's probably also useful for evaluation. I don't know any word for that. Do you have any?
No.
Okay,
but someone said it may use for evaluation in the future.
Yeah, so one example might be evaluate the success of a policy in simulation.
Yeah.
And then we need to consider the synchronic gap.
Autonomous driving, actually someone has done so.
Right. And yeah, I feel like it strongly depends on the synchronic gap. Right? For autonomous driving, the synchronic gap I guess could be smaller, but for example, for dextral manipulation or combined locomotion, right? Maybe it's like if the policy works super well in the simulation, it doesn't care much about how it works in the real world or something.
And any other questions?
I have a quick question. So I know one of the world model examples you mentioned was 3D plus physics. Do you have any good examples of world models that do that right now? 3D plus physics.
Yeah.
Do you have any good examples of a world model that does that?
So based on the framework of like a world model is a physically dynamic system. So any of the physics simulators, we can consider that as a world model. So if we consider world model is a model that the input is the current state and action, the output is the future states, right? And you consider like, for example, Isaac or Joko.
I see.
You have a state
Gotcha.
and you put action, it will get the future state.
Okay.
So that's kind of the world model.
Got it, okay.
I see there's one.
I remember you mentioned the future would be modular world model, and have you read any paper, or are you planning, or have you done any work, or what kind of work are you planning to do on modular role model?
Yeah, that's a good question. I haven't done any work, so that's why it's hypothesis. I'm thinking about doing some work on this area, but I feel like the first thing before we design the modular structure is to think about what information we really need for those robotics tasks. That will help us to understand what kind of module we need to have. So how many, for example, how much physics information we need, how much like 3D information we need, how much semantic information.
Thank you.
I had a question about the Arlo example that you brought up. In that, or no, it was the one before, not the Century one. The one with the drone.
Oh, this one.
Yeah. Is the replay buffer used to like update the world model as well, or like how does that work? Like is the world model trained offline and then plugged in?
The world model is trained in the loop. So like in the first stage, it will collect the data. So the data will be the current state and action for all the time step, right? And they use that data to train the world model.
So like after like the replay buffer is like filled, then that's used to train the world model.
Yeah, they use the replay buffer to train the world model.
But then after like the after critic training part, right?
Yeah.
There's probably also data that's updated for the replay buffer, right? From
Yes. So after the policy training, it will go back to the first stage, using that policy to collect more data.
Okay, interesting. Okay, very interesting.
Yeah, so I think there's obviously a lot of research work going on the world models themselves and model dynamics, what information to preserve, but more on the, I guess, the inference side, practical application of this. Correct me if I'm mistaken, but I still see a lot of world models using something like cross-complete method to actually generate the actions, which could be slow, limits the reactivity, especially for instance manipulation. So how do you see that piece evolving?
So you're saying like current models are more like kind of end-to-end? Is that, can you rephrase the question?
Yeah, I guess on the action planning side of the world model, usually you use like cross-entropy method to I guess minimize, the distance between your current state and your goal state, which practically could still be slow. So are there, I guess, faster alternatives to that? How do you see that piece evolving?
I see. Yeah. So a lot of methods are like using this kind of cross-entropy objectives to train the world model. Yeah. I think. Yeah. Even for that objectives, we can. So, from my perspective, like we will train like different modules, right? For example, in this modular structure, we can have like a different cross-entropy objective for different parts. One may be like the supervision on the semantic side, for example, more like a vision language model. One could be like supervision like on the physics side, so it's more like the RL, simple RL training. Yeah. So. It's more about like if you want to have a multi-objective that combines all the supervision signals, or you train separate models with separate supervision signals. A good thing I think also about like training modular one is that for different optimization problems you can leverage different data. So for example, if you train like the vision language model, right? You only need the vision language and action. So there's like actually more data you can extract higher from.
So, any other question? Okay, thanks Ming for the great talk.